So we're going to take a more in-depth look at quadratic functions. Anybody remember what a quadratic equation is? Hey, take it. What makes something quadratic? What about the expression of the equation makes it quadratic? I mean, you know what linear is, right? Huh?
1, 2, 3, 4 terms.
No.
No.
Think about exponents.
Up to the 4th power.
No. That'd be a quartic. It's 4th power. 3, 4. It's quadratic. What's the highest exponent in quadratic? Could look somewhere on the page too to help you.
2.
Yeah. Right. The highest thing would be x squared. Okay. Right. So if the highest exponent, if it's degree 2, right, it's going to be a quadratic function or quadratic equation. And do you remember what the graphs of these were? Yeah, it's definitely nonlinear, right? It's not going to be a line.
Rusty.
Yeah, Rusty. It's a shape like this.
It's going to be
Or
mirrored.
It is symmetrical. Remember what it's called? Starts with a P. No. Okay. Parabola.
Same thing.
Oh yeah. Right. A parabola. It can either be, like concave up or concave down, right? The way it opens up or down. Okay.
How do you spell that?
Parabola. All right. So this is the definition of a quadratic function, right? It's going to be something in the form of ax squared plus bx plus c. There's different forms of it that we'll get into later. No, it is not. X equals negative b plus or minus square root of b squared minus 4ac all over 2a. Any other questions? Okay.
Yeah, how'd you say all?
No. Lungs, diaphragm, pushing air.
Vocal cords,
Anyway, so it's in this form here, right? And they tell you, look what they say there.
A is not equal.
A cannot equal 0. Come back to that in a minute. But the important thing is that to be quadratic, the highest exponent will be 2, right? And any other exponents must be positive integers, okay? So it's going to have positive integer exponents, right? So if you have, say, like an x squared in it, and another term has like x to the minus 1, that's not quadratic. Or x to the 1/2 power, right? We haven't done that yet, have we?
No.
It's another way to do the square root, but anyway. So let's think about this here, where they say a cannot equal 0 and ax squared plus bx plus c. In part A, why is that important?
Because then you would have your leading term, your leading 0.
Right? And would it be quadratic anymore? Right? Because there'd be no x squared term, right? If a was 0, there would be no x squared term. And therefore, it can't be quadratic, right? X squared term. All right? Now over in B, thinking about the definition, quadratic function with the highest exponent is 2. And all other exponents are positive integers, okay? In part B, they want us to circle the ones that are actually quadratic. What about the y equals x squared minus 3? What's the problem with that? Where? What do you mean?
No, that's... Or does it have to be like that?
Exponents have to be positive integers.
That's a quadratic.
Yeah, that's quadratic. What about the x to the third plus 2x squared minus 4?
No, because it's greater than 2.
Yeah, it's degree 3, isn't it? That's actually called a cubic. So that's not a quadratic. What about this one here? Y equals x squared plus the square root of x plus 7. Well, I will tell you that another way to write the square root of x equals x to the 1/2 power. So that's not an integer exponent, right? That's another way to write that. So that is not a quadratic. Okay? And what about y equals 10 minus x squared?
No.
Why not?
It's negative x.
I will look, does that violate any of the...
Oh, never mind, it isn't.
Yeah, it is. That's quadratic. Okay? All right. Now, part C. They give us quadratic function y equals 10 minus 3x squared plus 7x. They want us to write it in standard form. You know what that means, right?
Yeah.
And then state the value of the leading coefficient. So, is the leading coefficient 10?
No, it's negative 3.
So it's not, right. So let's write it in standard form. It would be what? Y equals what? Good, negative 3x squared.
Plus 7x plus 10.
And the leading, I'll just say LC, the leading coefficient is what?
Negative 3.
Negative 3, okay? And you put it in standard form. Okay, so part D, now they have f of x equals 2x squared minus 3x plus 1. Fine, without using your calculator, f of negative 2. We've done this a million times, right? Just plug in that, so it would be, probably should be a little more room here, but, so f of negative 2 would be 2 times negative 2 squared minus 3. I got to square the whole thing, right? So I need the negative squared as well, right? 3 times negative 2 plus 1. So f of negative 2. PEMDAS, what do you do first?
Oh, so
So it's 2 times 4. Right. Yep, we'll do that in a second. And then what? Plus 6 plus 1, right? So that's f of negative 2 equals 8 plus 6 plus 1. I'll just do equals here. What's that give you? What is it? What's 6 and 8? 14? It's 15, right? Okay. So we had an input of what? Negative 2. And the output was? Okay, so they want us to write a point that must lie on this. Didn't we just find a point, like x comma y? So negative 2, 15, right? Remember input comma output, x comma y? Right, so if we plugged in that input and got that output, we know that that point is on the graph of this thing. Okay? All right, so what do they say down here? Oh, good. They talk about inputs go in, outputs come out. We know that already, right? But they're definitely different than linear and exponential. Remember exponentials? They kind of just go up like that, or they go down and never actually hit 0 kind of thing. It says the outputs end up repeating, right? For certain inputs, the outputs will just repeat, get the same thing, won't they? Careful. No. You got to switch. It's still a function, right? Because every input is going to have exactly one output, right? But you can have different inputs making the same output. So the outputs repeat. Somebody said something right at the beginning of class that relates to the outputs repeating, like when we graph this, like a parabola. What was it somebody said about parabolas?
Oh, you said that they go up.
But it was in a mirror?
Mirror, right? Isn't that called symmetry? Right, so if the graph is like all the outputs, right, from your inputs, are these outputs on this side of it the same as these outputs on this side? That's what they mean by a repeat. So that's where the symmetry comes in, right? Okay, and then every parabola, of course, if you've seen it, has what's called a line of symmetry right down the middle of it, okay, like a mirror. Okay, So we're going to start with the simplest, most basic quadratic function here. F of x equals x squared. And by the way, when you square a number, the result is always going to be what? Positive. Might that be a reason for repeating outputs?
Yeah.
Okay. So let's take a look at this table, right? So we have x squared. So we're going to take each one of these and square them. So input of -3, what's the output? 9.
9, 4,
Right, okay, just, okay.
1.
Yeah, 4, -1 squared is 1, and 0 squared is 0. And now what's going to happen?
It's going to be here.
Right?
1.
Right? Do you see the symmetry here now?
Yeah.
Right? Doesn't this right here kind of look like a turning point if you were to graph this? Maybe? All right, well, let's go plot these points and graph it. Now listen, when you graph these, it's supposed to look like a U, which means, is everybody listening? When you draw your line through, it cannot look like a V. Right? If it looks like a V, you don't get credit for it because that's absolute value. Okay? So let's plot these points. So we have -3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? And -2, 1, 2, 3, 4. -1, 1, 0, 0. And then, like when you go to the other side, you don't have to look back at the table, right? You're just kind of mirroring your points. Now let's draw a nice smooth curve through all of these. See how I make a nice smooth U at the bottom and not a V? And that's what that looks like. That's the very basic, simplest quadratic parabola there is. Just y equals x squared. All right? And by the way, this point down here, sometimes you'll hear it called a turning point, right? Because it's right at this point, the function goes from decreasing to what? Increasing right at that point, or it's called a vertex. Okay? And notice how it's symmetrical on both sides, right? Right? I could draw what's called a line of symmetry, or axis of symmetry there, right?
And then reflect it, and then it
Yeah, exactly. It's a reflection, which when you get the geometry, you're going to do a crap ton of those. Okay?
Oh, dear.
So, part C. So who remembers this? What's the range of this function? What is range? Remember domain and range? No, range is all the what? No, that's x. The only other thing left is what? Outputs, right? Or what values?
Why?
The y values, right? So what possible y values, right? It keeps going up, doesn't it? How far? Okay. Is there like a starting lowest y value?
0 to 0, and then the thing.
0 to infinity? Yeah, we could write it as 0 less than or equal to y less than or equal to infinity, but wouldn't it just be simple to say that the range is all y's greater than or equal to 0? Doesn't it also imply infinity? Okay? Remember, range is all the y or output values, and domain is all the what? Inputs or x. Outputs or. Okay. So yeah, these are all the inputs in the top row of the table, and down here are the outputs on the bottom.
This is what we did in like way before.
And like, oh, well, that's clear.
Like 5
Way before. Okay, so when we graph this, here's what somebody has how to spell it. Parabola. Some kids try to say parabola. You know, the parabolas, you can get those now at Sopranos. They're parabola with cheese or something, pepperoni.
What's a parabola?
I don't know, I just made it up.
Oh.
It's parabola. Kids pronounce it that way. Like it's some kind of Italian.
It actually, if you sound it out, it does look like parabola.
That sounds like
Only if you sound that incorrectly, right?
parabola.
The emphasis on certain syllables. Okay, so now we have a slightly more complicated, right, quadratic function. It's not just y equals x squared. It's y equals x squared minus 2x minus 8, okay? So now they want us to use our calculator to make a table of values. You guys remember to do that, right? Okay. So I'm just going to use a cat, and we're going to put it, so we're going to do some x's and some y's, okay? And you know, like with a line, how many points define a line?
2.
2. Do you think we could just use 2 points and accurately graph a parabola?
As a sum up.
Could you?
Yeah.
No?
No. It's at 4.
You need at least like 3 or 4, right? The more accurate you want to be, the more points you're going to need, right? So let's make a table of values from like -3 to 3. -2, -1, 0, 1, 2, 3. And we can just go to our calculator. Crank that out. Tab there. Okay. So it's x squared minus 2x minus 8. So x squared minus 2x minus 8. Hey, notice it doesn't sit right on the origin there, right? You see that? Okay. That's because it's not just a simple x, y equals x squared, right? It's other stuff
X
happening to
squared.
it. So we get a table by doing what? Menu. Geez, I wonder which thing. Oh, yes, table. Okay. So I want a -3 to 3, right? It would be 7, 0, -5, -8, 9. So let's do this here. So it's 7, 0, -5, -8 for 0. And look what happens. What do you notice about the table of values here? Yeah, where would be the turning point of this? 0, -8 would be like the vertex of this, right? Okay, well, let's go over and plot these then. So -2, 3, 1, 2, 3, 4, 5, 6, 7, and then -2, 0. 1, 2, 3, 4, 5, and 0. 8, bless you. And it's always nice when you get on the other side. Like, remember, you don't even have to look back at your table there. Now, this is going to be a tough one not to make look like a V, right? So looks like it's kind of narrow, but you do have to smooth out down here. So kind of. Okay. Wait, that something's not quite right there. Wait a minute.
Yeah, because it's not.
Yeah, no, I did. Yeah. What did I do here? Hang on. I'll fix this. It's supposed to be an eraser. So I should have, I just must have miscounted. 3, 7, yep. -3, 7. 2, 0, 1, -5, 0, -8. Oh, I know it. I just like immediately thought that. And then 1. Why is this not? It should be off a little bit, right? Why is it turning there? Oh! I know why. My table's not right. Jeez.
Yeah, that's what I was gonna say.
Yeah.
8 for 0.
So 0 is -8. And then 1.
-5.
Yeah,
0.
I just copied it wrong from my book here. We got it. So 1 is -9. There we go. Right? 2 is -8. And 3 is 7. I just wasn't using like a grid. So that kind of changes our vertex here, right? Where's the actual vertex now? 7, 0, -5, -8, -9, 8. No, good grief. What is going on here? Yeah, -3 to 5 is what we wanted. 5. Good grief. Now it's going to work. 7. That's why we don't do math in pen, right? 5 and 0 is -8. I'm not going to mess this up again. 1 is -9. 2 is -8. 3 is -5. 4 is 0. 5, 7. Now we're going. Anywho, let's try plotting that again. So that, those are right. Huh? What's on your calculator, isn't it?
No, my calculator messed it up.
Okay.
Or I messed it up.
Well, so we plot these. So we got -2, 0, 1, 1, 2, 3, 4, 5, 0, 8, and then +1 is -9. Now we start going back up, right? There, 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 one more in there. All right. Whoopsie daisy. Now this 1, -9, that's our turning point, our vertex, right? Now, I definitely want to sketch in the axis of symmetry. It's a line, right? Where would that line be drawn for symmetry here?
1. +1. Down the negative, or like the.
What would be the equation of this line?
X equals 1.
Yeah, what x does it cut through? The x, and where?
That 1.
So the equation for the axis of symmetry is x equals 1. And by the way, what are the coordinates of this vertex down here? Your table. 1, -9. What's the equation of the axis of symmetry? X equals 1. What's the x coordinate of the vertex?
1.
Yeah, otherwise known as a number I'm pointing to right now. So the axis of symmetry in this case is x equals 1. And that x equals, so the axis of symmetry always goes through the vertex. All right, you got that? And what do you know about the distances on each side of this axis of symmetry? What would you say, since it's a mirror? The distance on each side of that line.
7. 8.
Just generally, wouldn't they be the same? That's what I'm getting at, right, since it's symmetrical, okay? All right, so keep that in mind. All right, so now let's take the range again. It's going to be different than the range in the last one, right? What's our range? We'll flip the page back and see if you don't remember exactly what range is. Oh, come on.
From -10. -9.
Y. Wait,
Why do you keep saying X?
Y is going to -10 or -9 to infinity.
Just greater than? It doesn't include -9?
Or equal to.
Mm-hmm. So it's all the ranges, remember, it's all the Y values, -9 above. So we can say Y is greater than or equal to -9. That's the range. Okay? In other words, from -9 up to infinity. Okay, now look at part C. What is the domain? Wait, what's the domain?
X.
The X values over which it's increasing. Well, where does it start increasing? At what X value?
1.
Of 1, right?
1 to infinity.
1 all the way to infinity it increases, right?
Yeah.
Okay, so in other words, at X greater than 1. Why am I not going to use equal to? When it's actually at 1, is it increasing?
No, it never gets to 1.
Yeah, it does.
Wait, what? No, it's not increasing because it's already out.
Correct, yeah. And that 1 is the turning point, right? So it's right at that very point, it's not decreasing, so that's why I have to leave out the equal sign. And I think the book doesn't do the best job of being consistent with that, but I'm going to try to be, okay? So domains, or range is all y values, domain is x values, right? All right, so part A, state the coordinates of the parabola's turning point. Well, we already did that, right? The vertex. We did that, it's in the graph. What are the coordinates of that vertex, everybody? Everybody.
1, -9.
Okay, wow. And part A, they said draw the we already done that. Draw the axis of symmetry. We did that, right? Goes through the vertex. And write the equation. What was the equation of that axis of symmetry? Everybody, because you wrote it down when I did, right? X equals 1. Right, what x does it cut through? X squared at 1. Okay? And again, notice axis symmetry 1, vertex x coordinate 1. X equals 1. This x equals 1. It's the same x. Okay? All right, now they want to know the x-intercepts of this graph. Right? Now, when you see the terms x-intercepts of a graph, you can also say to yourself, well, they mean something called the zeros or the solutions to the equation. Okay? So now, why would they call the x-intercepts the zeros of the graph? Yeah, whenever it crosses the x-axis, the y values, the outputs are 0, right? And how many times does that happen in this graph? Twice. So how many zeros does it have? 2. 2 x-intercepts, two solutions, right? And by the way, when you take the square root of a number, how many answers do you get?
1.
Remember, we don't use it all the time. When you get 2, positive and negative of it.
Oh, yeah.
Like, what's the square root of 9? 4. Negative 3. 3 or negative 3. What's 3 squared?
Oh, I think it's 4.
9. What's negative 3 squared?
9.
Also 9. You square something that's positive, right? When you take the square root, you get 2 answers technically. That's why there's 2 zeros on this. So the x-intercepts will be found at x equals what? Negative 2. And very important here, I put the word or. X equals, what's the other one? I don't think it's positive 2. Look at the graph. That's the first one we just listed. There's the other one. That's a x equals what? 4. So x equals 1 or x equals 4. Okay? And so the coordinates of this intercept would be what comma what, guys? For next negative 2. Negative 2 comma 0, because the y is 0. What are the coordinates for this intercept? 4 comma, hey, the y is 0. So they call it the zeros, right? Right? So these are where they're where the function, the output equals 0. Okay? They are where the function, right, and its graph is all its outputs, right? Outputs equals 0. All right? So whenever you see x-intercepts, you can also think of the word zeros or solutions to the equation. Right? Okay. Let's go to exercise 4. Now they've given us a quadratic function f of x. They didn't give us the actual equation, right? What did they give us? The table of it, right? So it's kind of represented here. So here's our table, inputs. The other column is the outputs. And they want to know, what are the coordinates of the turning point? What's another name for turning point? Vertex. So do the outputs in that table look symmetrical? Do they? They don't? The outputs. Look at the outputs. 4, 9, 12, 13, 12, 9, 4. You threw another one on the end there, right? Yeah, it's symmetry, right? So this is like the graph, this one I believe goes like this, right? And it repeats, but facing down, concave down. So what would be the coordinates of the turning point? Where's the turning point here? At 2, right here, right? That's it. So the coordinates of our turning point are 2, 13. That's where turning point is where it switches from increasing to decreasing or vice versa, right? Okay. Now let's think about this. What is the range of this function? Y values. Well, we're going to assume that we can keep the table going, I guess. So we're saying okay. I'm going to give you guys less than or equal to, yeah, less than this time, isn't it? Because if this is the turning point, right, wouldn't this thing look like that? Right? And now it's facing down. So instead of a range being greater than or equal to something, it's going to be what? So y, a range, is less than or equal to what? You sure? I'd say 13, right? Because look on both sides of 13. 13 is the highest value, right? And what do the numbers do on both sides of 13? They go down, right? So this thing is doing this, right? Okay? So up here's your 13, and then it's going down equally on both sides. Symmetrical. Okay? So that's kind of a brief little intro to quadratics and parabolas. Let's look at some Regents questions now. Okay. A couple ways you could do this first one. So did everybody read this? Is there a key word in here? Not. So which of those points is not on the graph? And those are all inputs, comma, outputs, right? Well, what's annoying about these problems is, as much as I hate guess and check and multiple choice, they design certain ones to precisely be guess and check. So what you could do, I'm going to explain this to you, and then I'm going to give you all a nice, easier way to do it. All these here that I'm underlining, you would agree, are inputs or X's. You can plug them all in and then see if this is the thing that comes out, or that's the thing that, right, that results in plugging that in. Seems kind of annoying, but we could also use our calculator, couldn't we? And graph it and trace, right? Let me show you how that works. So let's take this thing and put it in our graphing calculator. Let me get rid of this table. So menu, to remove table. Okay. And then I want to get rid of this stuff. So tab, up to that, control clear. And what was that? Yes. 3x squared minus x, no, I took it off. Well, when I hit enter on here, it'll delete that. I deleted the table, or entry. Plus 7. It doesn't even show up on there, right? So here's what we can do. The graph is somewhere not on this. Like, we'd have to open up the window or something to find it, but watch what I do. Remember how we can trace a graph? It has like a little cursor going along it. So let's hit menu. What choice do you want to use, guys? Trace, and then just graph trace. Oh, okay, so there it starts, right? Now, instead of tracing the graph, what I can do when it's in this mode is just type in a number for the x value and hit enter. right? So what's that first choice in the multiple choices? Negative 1.5, comma. So if I input negative 1.5, it should output a 15.25. Let's find out. So right when it's in this trace mode, I type negative 1.5, enter. Look what it does. What's the output? Right? So choice 1 is good, yeah? And now, don't have to touch anything. Is it? I thought that was TV. I thought that was you walking out.
Oh, yeah.
Yeah. So let's check the second one. 0.5. 0.5. Enter. Do we get what they have in choice 2? 7.25? Okay. Let's check choice 3. 1.25. What do we get? All right, so this was choice 3.
That's wrong.
Yeah, it's not quite what they have there, right? They have what, 10.25, and it's really what? 10.44, wouldn't it be?
Yeah.
Yeah, so that would be our choice. Come on.
Might have been like a. Okay.
Anyway, so really it should be 1.25, comma 10.44, right? So that's the one that's not. For what? Very passionate about this, I don't know. Okay. Now what do we have in number 2? Just 2 things? Well, why don't you start by reading from the very beginning?
The functions f of x, q of x, and p of x are shown.
So how many functions did they give us?
3.
In 3 different forms, right?
Yeah.
They have f of x as a graph, q of x as an equation, and p of x as a table, right? All right, so what's the question?
The input is 4. Which functions have the same output?
All right. So we have to check them all, yeah? So how are we
F
gonna?
of x and p of x, because if you go to the x,
So let's go out to 1, 2, 3, 4, right?
1, 2, 3, up
Input
to
of 4, and you go up to hit the graph at what?
it's f of x,
Okay, so that one, yep.
and at 4, 3.
And over here, input of 4, output of 3, so there.
X.
But what about q of x?
We gotta do the extra work.
Yeah, what's the big deal? So let's put a 4 in for q of x. So q of 4 would be 4 minus 1 squared minus 6. So you guys tell me. Hopefully we end up getting there. All right, so this one's also 4 comma 3, right? Well,
-1.
no.
Hold on a second. 3 minus 6, it's 3.
3 minus 6 is
Oh, I got
not 3.
0.
What's 4 minus?
It's negative 3. 3.
4 minus 1 is 3. 3 squared is what? 9.
No.
So it's 9 minus 6, which is what?
Equals 3.
Oh, so this one was also 4 comma 3, right? So what's our answer?
Number 4.
Yeah, all of them. There we go. So be ready to,
Yeah.
work with like any form of a function they give you, right? Graph, table, or equation. On to number 3. Now they're using a slightly different, they're using an interval notation we haven't been using in a while, but, okay, take a look at this. X squared plus 2,
Oh, I forgot.
the
what this
range.
is.
Well, okay, so do you remember
Oh,
the hard
not
bracket
included.
means
Okay.
included, and the soft parentheses means not included, like up to that point, right? And can you ever include infinity? No, because you'll never read, right? So always infinity has got not included.
So you can cross these ones, the ones that have this
hard one. Wait, never mind.
Yeah, just for a second. Hold on. Now, listen. I want you to think that there's another way we can do this, but I'm going to have you think ahead of another section or two here. This is x squared plus 2, right? Now, let's say it was just x squared. You remember that graph from the notes? That was the most basic parabola. And where was the vertex for that?
0, 0.
Yeah, I mean, forget, look back at the first example in our notes where we graph that thing, y equals x squared, right? Everybody go look at it right now. Look back and look. Because we've kind of thought about things like this way before. So you see that first graph, and the vertex is right on the origin, right? It's concave up, goes up to infinity. And what was that range? It went from y greater than or equal to 0, right?
Yeah.
Okay, just before we do this kind of the cheat way, if I take that very same graph we're just looking at and think of the table of values, adding 2 to everything in the table of values, in that table that we had there, what do you think that would do to that whole parabola in that graph?
It's just gonna move it up.
Wouldn't it just shift it up 2 units?
Yeah.
Right? So, instead of being right here with the vertex,
Yeah.
wouldn't it be more like this? Yeah?
Yeah.
And so what would the actual range be?
Infinity, 2. To infinity.
Well, not negative infinity, there's nothing down. We're gonna,
Oh, so it's number 3.
well, really, okay, it would be y greater than or equal to 2, wouldn't it? Instead of 0? But another way to write that would be what? 2 to infinity. But what kind of bracket on 2?
R.
Yep, and on infinity? Right? So which choice is that?
3.
Choice 3. Now the other way you could do this, or use your calculator. You could just take that, punch it into your calculator, look at the graph, right? And see where that vertex is. And see that all the y's are greater than or equal to 2. Right? But I'm kind of glad we thought of it this way, because I know we talked about this a little bit before, but later on we're going to talk about shifting these things in more detail. So that'll warm you up. I think this is the last one, right? IS. What do we have to do here? Read it. Tell me.
Graph y equals f of x and y equals e of x opposite of x.
Look at you guys, starting from the beginning of a sentence. Finally. Okay.
Determine all siblings.
So go ahead and do that then. What type of graph will be f of x? What will it be?
Quadratic.
Yeah, or parabola, right?
Yeah.
And what about g of x? What's that graph going to be, everybody?
Linear.
Yeah, that's mx plus b, right? Right? We could graph that one, or you might want a straight edge for that one. I don't know, that'd be handy. But what's the follow-up question?
Determine
Oh.
the values of
Where f of x, now when we graph both of these, where do we find where they're equal to each other? If they're both graphed. We'll see for you.
their intersection.
Yeah, it's where they cross the intersection, right? Well, linear one should be pretty simple to graph, shouldn't it? What's the y-intercept? So we go up to 3. And what's the slope? Right? So the m equals -2, 1, down 2, and right 1, isn't it? 1, 2, right 1. We'll do it a couple times. That, just to be accurate, and take your straight edge too. I'm on a double arrow, I think. Yes. Yeah. There we go again then, huh?
Wax is 3. Oh, wait.
I think I'm pretty close there. All right, so now for the other one, I'm gonna need a table of values, yeah?
Yeah.
So we'll do, oh, thingy. And you can use your calculator to get this, right? And you probably want to kind of figure out what the turning point is when you look at your calculator and center your table around that. So go ahead and put the f of x in your calculator, clear out the other thing, yeah? And then when you make your table, you want to have like the turning point, the vertex. Listen, everybody stop a second. Have the vertex in the middle of the table and have like 3 or 4 points before and 3 or 4 after it. Right? And you get that nice symmetry. Does that make sense? So punch it in, pull up your table, and find where that vertex is. I have to adjust the window there. So 2x squared. That's 8x plus 3. Yeah. Now I want a table to copy some points down there, so I go menu, table, sure. Remember, you're looking for the symmetry, right? You're looking for that turning point. You have numbers like they're same on both sides with a different number.
What number do you want us to go from? Like negative?
Well, like I said, look at the table. Figure out what one is the turning point, and that's what you put in the middle of your table. Where's the turning point to this? So let's look at what we got here. -3, -5, 3. So like, whoa, no, we'll do that. God, come on. Now it's just not gonna.
There is enough space to put the negative for the.
So we got -1 is at 13, 0, 3, 1 going to -3, -5. Oh, what's it doing now? Do we see a turning point by any chance? Where's the turning point? Is it?
4.
What? 2 -5.
How? It's still a negative right after that.
Look at both sides of -5. They're the same. So it goes 3, -3, down to -5, then back up to -3, back up to 3.
What the heck?
Right.
What's the deal with that?
With what?
Oh,
The vertex, the turning point. Where it's symmetrical, right? You guys told me the numbers start repeating, right? So 2 -5 is what we put in the middle of the table. Right? So I want to have 2. How do I do this, right? This is my vertex. So now I need I want I don't know, 3 points on either side. So give me some points before 2. 1, 0, -1. Give me 3 points after 2. 3, 4, 5. You see how I found the turning point? So now when I plot, it's nice and symmetrical.
Is it 5 I only did 2 points on each side?
You should do a little more, especially, right, because then, as you go try to draw your line after that last point, you're not going to be accurate. Do at least 3. So from your calculators, you have, 13, 3, -3, and then it's going to repeat, right? You see what I mean about that's the turning point right there? Look on both sides. Starts doing the same thing. Okay? So let's go plot our points. You don't have to copy them from up here because it's in your calculator. Okay? So I'm not going to feel guilty about standing in the way. All right. So we want 1, -1. Here at that's 13. And then 0, 3. Oh, it looks like we found a point already, right? 3. And then 1, 1, 2, 3. So we're at 1, -3, and then 2, -5, and then 3, -3, and then 4, 3, and 5, 13. So this is, we should have here, don't make it a V. Okay? Notice it's hard to say I have arrows, not even on this line, it's right, gotta have those there. So you guys seem a little hesitant on that value where there was symmetry in the table. You understand that?
Yeah.
Right, you're looking at the outputs, you're gonna find an output that's got the same number on both sides of it, okay? Going in different directions. And that's what you want to start with here on your table, okay? All right, so what are the coordinates of where the two functions are equal?
1, -0, 3.
Right here at 0, 3, and where else?
3.
3 what?
3.
3 what?
3 -3.
That's 0, whoops. 0, 3, right? So to answer this, we will say f of x equals g of x at what? 0, 3, and 3, -3, where they intersect. All right. Okay, that was the last one.